All right, this is going to be a modified version of the MCS, Microblaze MCS tutorial, first developed by Jim Duckworth at WPI and revised somewhat by Kurt Wick at UMN in moving from Vivado 2015 to 2016. I have already done the initial steps and am presenting information similar to what's on page 1. I have created the top level file name mcs_top.v. These are the primary IOs on the signals. One difference is that I have used the name FPGA_clock. Theirs is clock_FPGA. I am using 4-bit switches and 4-bit LEDs, which somewhat changed the ground game here, but we'll get to that a little bit later. So the first thing that is done on this is to get moving and click onto the IP catalog. IP catalog comes right up. We're looking for the, see if I can spot it, embedded processing right here. We specifically want to go for the processors, go down here, find Microblaze MCS, click on that, and we're kicking it off. And it presents a window like this. This used to be called the wizard. Note that in 2016.4, this tab board is present, which is not present on their 2016.2 version. We're going to proceed over to the MCS tab and act as if board did not exist. Our clock is not 100 meg, but rather 125. We're going to pick a memory size of 32K. Get that right. We're going to keep the area as described before. We're going to select a UART. We want to enable both a receiver and a transceiver. We're going to keep the 9600 8 bits and even. And the next thing we're going to do is go over and select the GPO outputs, and that will be for our LEDs. We're only having 4 of them, so we're going to select 4. We're going to pick general purpose inputs. We're going to use them. We're going to have 4. They're going to be our 4 switches. 4. And at that point, I believe we simply hit OK, taking us into page 4 of the write-up. It's okay to create the directory. Yep, it's going to generate output products. We're going to basically say generate them. For the write-up, it's okay. The out-of-context module one was created. That's good. If we re-examine our design sources, MCS top is back here, and below that it is Park, the Microblaze MCS. This is the core information that we just created. Okay, it's created the products for us that we need to have. The main element that we're after, however, is in the IP sources. We want to get the instantiation template. It provides both a Verilog and a VHDO. The VEO is the Verilog. Click on this, expand this window, come down here. We're going to snag it. Copy. Go back up to the instantiation, not there, back into here. Go into the top.v. We're going to park it down below here. Paste it in. Now we need to change our instance name to match theirs. We need to now reassociate the primary I/O signals to the signals on the module. This one here is not cap clock, but FPGA underscore lowercase clock. Cap reset becomes lowercase reset. UART RX becomes just RX. UART TX becomes just TX. 1, 2, 3, 5. The inputs become the switches, which are SW. The outputs are the LEDs, which is just LED. Should be able to hit File Save on that right here. And if my typing has been accurate, shouldn't be an issue. So now we've created the design. We've bound the IP instance to the names. We should be at the point of about page 7 on the write-up, just as a point of tracking. And we should be able to run synthesis. And if typing was accurate, it should be okay. Synthesis completed. Let's view the reports for a moment here. The write-up said we should have had 590 warnings, and it looks like I have only one warning. Either way, it said to ignore them. I'm going to chalk this up to my superior typing, but the reality is probably that this is using Vivado 2016.4 versus their version, which was 2016.2. So the next step is to do File, export the hardware, and we don't have a bit stream yet, so we won't include it. This is going to produce a package of files that go over to SDK, and that's our next step, which is to basically hit File, launch SDK. And it'll be local to all this. I'm going to minimize Vivado at this point. And we watch SDK coming up. When SDK finally settles out, it should resemble the top graphic on page 9 of the write-up. This is the part where you have to be patient. As I said, this should resemble page 9 of the write-up, and it's showing the HDF. Now we're going to create a new program. We're going to go File, New, Application Project, and we've been assigned to give the name Hello World. Use the default location. It's a standalone OS per the write-up. MCS top hardware platform. It's a Microblaze. It's going to be create a new for Hello World BSP, and the next step is simply to click Finish. So we see it's created some sub-projects over here, the MCS top hardware platform, Hello World board support package, and Hello World. Let's open that one, look down into sources, click on helloworld.c, see the familiar code. This came out of a library that's on board, which has a number of pre-configured write-ups. Notice if we look down in console that when we did this, it automatically created from the source file which it developed, and it created a .elf file, which is basically what we'd like to have happen. Now we go back to Vivado, and we go into Tools, and we click on Associate the ELF files, and per the write-up it says continue. And this popped up. Now we need to look into here, and we want to click on Add Files, and it's going to have us we need to browse into our directory, and the directory is under the XUP and so forth, so it's going to be a bit of a browse. So I've got to go on to C, go down to XUP, go into here, go into MCS top, go into SDK, go into Hello World, go into debug, and finally find hello world.elf, which has been selected, and we select OK. And at that point we also select OK here. We note that Hello World is associated with that, and we're good to go. So at this point we click OK, and we should see the ELF under the design sources right here, hello world.elf. Got one more thing to do here. It's important. We need to add sources. We're going to add a constraint, and it's one that's parked on my desktop. And so we need to say add the file and find it on the desktop. And it's this file right here. And we're going to say OK to that and finish. Now let's take a look at it, the constraint file. the constraint file was constructed from the original Zybo master. A number of things have been changed. Where it had the clock, I inserted the project clock, which was called FPGA_clock. It needed to go into two different sites. The waveform for the clock is for 125 megahertz with a cycle of 8 nanoseconds, half on and half off, as shown here. Then I've got my input ports on switch 0 through switch 3. They're all assigned per the actual hard connections on the board. I'm using button 0 on the Zybo board to be the reset input. And I'm also, let's see, I'm using my LEDs, LED 0 through 3. They're landing on the hard board level connections. See, I think let me see if I can find reset. Control F. I've already reset. Yeah, reset is on button 0, and then the next one I wanted to have is I wanted to say where is Control F TX. So we got that. Excuse me. No, got the wrong signal name. I'll find TX down here. TX return, and you'll notice that TX and RX are on a couple of pins. If you step back up, they're associated with PMOD header JE. I'm going to minimize this for a second and try and show you where that comes from. The PMOD I'm using is one of the digital ones that looks like this. You jam the USB in here and this plugs into the PMOD slots, but it doesn't have anything labeled at this point as to what the signals are. You'll need to have the PMOD schematic, which we'll click into view here better, and should be noting that the TX pin comes down and hits into pin 3 of the J2 connector. Pin 2 goes over to the RX pin, and so I now know where TX and RX are for this guy. I need to then make sure that my Microblaze UART has a TX to RX, RX to TX, so that one transmitter goes to one receiver and vice versa. Now, one last thing is on the Zybo connector. This is the JA PMOD, JB, JC, JD, and JE. This is the one that has the A to D converters on it, and these three all have high-speed signals. This is the only one that has ordinary type IOs on it, and so it's like 3.3 volt and so forth. The PMOD is shoved into the top row of this connector, and then its rear end with the USB is sticking out over here. So we're going to have a USB into this port, which is going to program the bit stream, and another USB into this port, which is going to be doing the communication with the terminal that we'll be using. So we go back to here. We've made the association of the constraint file, and so we still need to do a few more odds and ends. One of the things we have to do is we need to run implementation, and we need to generate the bit stream. We can actually do that in one move by simply saying generate the bit stream, and launch it on the local host. Synthesis is out of date. Do all the steps in between that it needs to. It's out of date because we just added the constraint file. Alright, at this point we've had completion of the bit stream and compilation, etc. We could go directly to opening the hardware manager. I'm going to actually just say to view the reports. We'll look over here at this summary real quick. You'll notice that it does list some warnings, 72 of them. The write-up said it would have about 100, and we could disregard those. One other thing I need to do at this point, and that is I've got the board plugged in, but I haven't got it powered on. I'm going to minimize this, and I'm going to open the device manager. So I click on device manager. I'm wanting to look at the COM ports, and you'll notice it's got 10 down to COM 7, and then it notes USB serial COM 24 is on here. That's actually being powered off the port, and it's plugged into the board through the PMOD. I'm going to turn the board on. And when I do it, it now powered up the JTAG controller. So this is basically the port that we're going to be programming through, and this will be the port that we're going to be communicating with for our little test design there. So now that we know that information, we don't need this. COM24 is where we're going to go. We're going to go back to, might as well also, while we're here, let's find and kick off PuTTY, which will be our terminal supervising program. We're going to use a serial port. It's going to be on COM24, as we just noted. It's going to, let's see, I'm going to define it here, 24, 9600, 81, none. I'm going to set it for no flow control. I'm going to go back to the terminal. I want to have implicit carriage return and line feed. Likewise, line feed with carriage return, and turn off that and that. The keyboard looks okay. So I'm going to click open and go back into Vivado, open the hardware manager, open the target, do auto connect. Now I wish to program the device. Yep, I want the Zinc XC7Z010. That's the one I want. The file I want is MCS_top.bit. I hit program. I got a green light indicating that the file downloaded and should be running. I have hello world. That's good. I go make sure that it's good by punching button 0, doing a reset, starting over, button 0, reset, start over. So we're done with that phase. Per the write-up, we now need to make some changes. So we go back to SDK, inspect the original source code for the program here, find the target. This little chunk here was the primary one. We're going to modify that, be a little more original than they were. We're going to copy the title of the 1962 45 RPM hit by James Darren. And his hit song was Goodbye Cruel World, which is along a similar note. We push that note down here on the console that it's automatically creating the new ELF file. Now we go back over to Vivado. We've done that. It's automatically done an overlay. Vivado notes that our write bit stream's out of date with the change we just made in our design directory, so we now need to go back to generate a new bit stream and launch the runs on a local host. We don't need to actually view the reports or anything, but we'll say, okay, what the devil. So the next step we need to do here is, again, we've created the new bit stream. We should be able to just go program the device with them. 7210. Again, MCS top.bit. Hit program. When I do that, my green light went off, my green light came on. If I'm in luck, I will see the new message over here, goodbye cruel world. Make sure I'm going to hit the reset button. It repeats, it repeats. All right, we're going to go back once again into SDK, and this time we're going to take and copy this section of code, which is a section on page 16 of the write-up. This will be our last little experiment, so I'm going to close this. And I'm going to basically take out the code for the whole Hello World endeavor here. I'm going to do a delete, do a file paste, again do a file save. See, save is here. And again, we see it's auto creating the ELF file. That should be complete. Go back to Vivado. Now in this particular write-up, it basically is going to spit out a slightly different headline, and it's going to be reading the slide switches and then outputting them to the corresponding LEDs. You won't be able to see that on this display, but you will be able to see the headline come out. So we've done that. We've noted the bit stream's out of date. Create the new one. Again, we'll just basically say open the reports. We don't care about that. We now have a new bit stream. We're going to basically say program the device. Same part. Same design top. Hit program. Green light went out. Green light came on. Close these two. We see the new message saying reading switches, writing to LED ports. Go over here. I'm going to verify. Trust me that I am doing it. They are working. Now there's one last section in this lab where they have you read the read the LED, or excuse me, read the switches and write the LEDs, but they do some other fancy calculations, but they're using the smaller, supposedly smaller footprint of printf or whatever the XIL version is. And we're going to leave that as an exercise for the student and call that one a basic completion of this lab. And we're done.